Welcome to G Fun Facts Online. Imagine trying to run one of the largest empires in history, managing millions of people across treacherous mountain terrain, tracking harvests, armies, and the stars themselves, all without ever writing down a single word. That's the puzzle of the Inca Empire. For centuries, we believed they were a civilization without writing. But what if the writing was there all along? Not in ink on paper, but in the intricate twists and knots of colored strings. Today, we're untangling the mystery of the Khipu, an ancient Andean communication system that is being decoded right now, thanks to the power of modern computers. We're discovering it wasn't just an accounting tool. It might have been a three-dimensional language capable of telling stories, recording laws, and preserving a history we thought was lost forever. The Khipu, which means knot in the native Quechua language, was the primary record-keeping device for the Inca Empire, which flourished from the 1400s to the 1530s. But its origins are even older, dating back to the Wari Empire around 600 CE. A khipu looks like a piece of textile art. It has a main, thick horizontal cord, and hanging from it, like fringe, are dozens or even hundreds of smaller pendant strings. These pendants can have their own smaller strings attached, creating a complex, cascading structure. The people who made and read these were called khipu, or knot makers. They were the highly trained scribes and administrators of the empire, and they encoded information through a series of very specific choices. They chose the fiber. Was it cotton or wool from an alpaca or llama? They chose the color, using a vast palette of natural dyes. They decided which way to spin the thread and which way to ply the finished cords together. And of course, they tied the knots. For most of the 20th century, we only understood a fraction of this system. In the 1920s, a historian named L. Leland Locke made a huge breakthrough. He figured out that the knots on most khipus were numbers. The Incas used a base 10 positional system, just like we do. A simple knot might be a 1, a long knot with 4 turns would be a 4, and a figure 8 knot could be a 1 as well, depending on context. Crucially, the position of the knot on the cord told you its value. A knot in the lowest position represented the ones place, the next one up was the tens, then the hundreds, and so on. This was revolutionary. It proved that the Incas could conduct massive censuses, manage tribute payments, and track warehouse inventories with incredible precision. Spanish conquerors even noted that khipu could bring their knotted records to colonial courts, and they would be accepted as valid legal testimony. But this was only part of the story. What about all the other details? The vibrant colors, the different fibers, the direction of the twists. Spanish accounts were confusing. Some said the khipus recorded histories and poems. Others dismissed them as simple memory aids. The devastating truth is that we may never know the full extent of their use. During the conquest, the Spanish destroyed countless khipus, burning them as objects of idolatry. Of the hundreds of thousands that likely existed, only about 1/400 survive today, scattered in museums across the globe. For centuries, it seemed their deepest secrets, their narrative potential, had been turned to ash. But then came the digital age. The problem with studying khipus manually is their sheer complexity. With thousands of combinations of color, fiber, spin, and knots, comparing them by hand is nearly impossible. So researchers decided to turn these physical artifacts into digital data. This effort was pioneered by the Harvard Khipu Database Project, started in 2002 by anthropologist Gary Urton and Carrie Brzezin. They began meticulously cataloging every single detail of the surviving khipus. The length and color of every cord, the direction of its spin and ply, and the type and value of every single knot. This work has now evolved into the Open Khipu repository, a massive open-source database that allows scholars to run complex statistical analyses across hundreds of khipus at once. They can ask questions that were unthinkable before. Are certain colors always tied to certain numbers? Do khipus from a specific region share a common structure? Using data science tools like machine learning, researchers are now sorting khipus into different categories, almost like identifying different genres of books. They can even spot mathematical relationships between them. In one incredible case, this digital approach allowed them to identify two khipu fragments, housed in completely different museums, as belonging to the same original artifact, digitally stitching them back together. For decades, the dream of every khipu researcher was to find a Rosetta Stone, a khipu that came with a direct Spanish translation. That hasn't happened yet, but we've found the next best thing. The breakthrough came from a collection of 6 khipus from the Santa Valley in coastal Peru. These khipus were from the colonial era, made around the 1670s, and they were found alongside a Spanish census document from the same time and place. The project was led by a then Harvard undergraduate named Manny Medrano. The Spanish document listed the names of 132 tribute-paying villagers who were organized into 6 clan-like groups called Alas. When Medrano and his professor, Gary Urton, examined the 6 khipus, they found they contained a total of 133 pendant groups, an almost perfect match to the 132 people in the census. That was just the start. They discovered that non-numerical features of the khipu directly corresponded to social information in the written document. For instance, the way a pendant cord was attached to the main cord, either facing forward or reverse, seemed to signify which of the 2 main social divisions or moieties a person belonged to. Even more exciting was the color. The intricate color combinations of the cords seemed to act as unique identifiers for the 132 individuals on the list. The colors didn't spell out names phonetically, like letters in an alphabet, but they functioned as unique labels. This was the first concrete proof that the physical construction of a khipu, its colors, its structure, encoded complex, non-numerical, narrative information. It was more than just a ledger. It was a registry of a community's social fabric. So if khipus can hold narrative information, how do they do it? This is where the detective work gets really fascinating, and 2 major theories are leading the way. The first is Gary Urton's binary code hypothesis. Urton proposes that the khipu is essentially a 3-dimensional, 7-bit binary code drawing a direct parallel to modern computers. He argues that at every step of making a khipu, the khipu kamayuk made a series of binary, either-or choices. There are 7 key choices. 1. Was the material cotton or wool? 2. Was the cord dyed a light or dark color? 3. Was the fiber spun to the left or the right? 4. Were the threads plied together in a left or right twist? 5. Was the knot itself tied with a left or right twist? 6. Was the pendant cord attached to the main cord in a forward or reverse direction? And 7. Did the knot represent a decimal number or something else? If you combine these 7 binary choices, you get 2 to the power of 7, which is 128 unique coded units. Urton suggests that when you add in other variables, like the 24 distinct colors the Incas used, the system could have contained over 1,500 discrete information units. That's more complex than Egyptian hieroglyphs and on par with Sumerian cuneiform. In this view, a khipu isn't just a record. It's a physical manifestation of a logical system, a woven computer program that could be read by anyone who knew the code. A second, equally compelling theory comes from anthropologist Sabine Hyland. Her research focuses on a pair of 18th-century khipus that were secretly guarded for centuries by the villagers of San Juan de Colata, Peru. According to village elders, these weren't accounting records at all. They were narrative letters exchanged between local leaders during a rebellion against the Spanish. Hyland's analysis, which involved not just seeing but also feeling the cords to distinguish between 6 different types of animal fibers, suggests these khipus work as a logosyllabic writing system. In a logosyllabic script, symbols represent phonetic syllables, not individual letters. Highland identified 95 distinct combinations of color, fiber type, and ply direction, a number that fits perfectly with the range of known logosyllabic scripts around the world. Working with the village's oral history, she has even proposed a phonetic decipherment for the names of two of the kinship groups mentioned in the letters. The theory is that the specific colors and animal fibers were chosen because their names in the Quechua language sounded like the syllables of the lineage names. For example, the Quechua word for blue, ancas, might represent the syllable an or ka. If Highland is correct, it means the Inca may have possessed a form of phonetic writing, a system of